Okay, continuing on with our gas review worksheet. 18. We have a liquid that is vaporized under the given conditions, and it tells us the empirical formula of this liquid is CH2, and we want to know what is the molecular formula. Okay, so the thing to remember is that for the molecular formula, to find that, we need two things. We need the empirical formula, and we also need the molar mass, the actual molar mass. Alright, now the problem told us that our empirical is CH2, and molar mass units I'm looking for are grams per mole. Okay, so I have grams given as 0.72, and what I need is to know how many moles are associated with that number of grams. So let's see what I've got. I have a pressure 0.967 atmospheres. I have a temperature 110 into 73 is going to be 383, and I have a volume 0.559 liters. Alright, so we can find the moles. And this gives me 0.0172 moles, which I'm going to substitute that in up here, which gives me a molar mass of 41.9 grams per mole. And then what I want to do is my empirical is CH2, and its mass is around 14 grams per mole. So I want to see how much bigger my molecular formula is going to be than the empirical. So I'm going to divide my molecular mass by the mass of the empirical, and that comes out to be approximately 3. So my molecular formula is C3H6, which is choice C. 19. We have gaseous C2H4 reacts with oxygen according to the following equation, and for some reason that's missing off of the slide, but you have that on your handout. And it wants to know what volume of oxygen gas do I need to react with 3.23 moles of the C2H4. Okay, so C2H4, I'll write the equation here so we can work with it. 2CO2 and 2H2O. And it says I want to know this volume. It says I'm at STP. We'll assume all the gases are at STP, or both reactants in this case. I have 3.23 moles of the C2H4. So 3.23 moles C2H4 and 1 mole C2H4 to 3 moles of oxygen. And at STP, 1 mole of gas is 22.4 liters. So times 3 times 22.4. So I'm getting 217.1 liters. So answer C would be correct. All right. Calculate the density of nitrogen at STP. Alright, nitrogen is N2. Think of the units. Density is a mass per volume. Okay, since I know it's nitrogen, I know that the molar mass is about 28 grams per mole, and I can use that grams, 28 grams for my mass, as long as when I find my volume that I use 1 mole. And remember that 1 mole at STP is 22.4 liters. That's the volume. I'm going to plug in up here, and that would give me a density of 1.25 grams per liter, which is answer D. A 3.31 gram sample of lead nitrate is heated in an evacuated cylinder with a volume of 4.06 liters. Salt decomposes when heated according to the equation, and again, the equation did not transfer, but you have it in front of you. And so assuming it completely decomposes, what is the pressure in the cylinder after decomposition and cooling to a temperature of 300 Kelvin? We're going to assume our solid lead oxide does not take up very much volume at all. Alright, let's put this equation up here. So we're decomposing the nitrate, and we're going to get the oxide and nitrogen dioxide gas and oxygen gas. And we have 3.31 grams, molar mass 331 grams per mole. Alright, so first thing I'm going to do is let's find out how many moles. Alright, so I have 0.01 moles of my lead nitrate. Okay, then now let's find out how many moles of gas will be generated, because here all we care about is the gas, because that's what's going to cause the pressure in the container. Alright, so I have 0.01 moles of lead nitrate, 2 moles of lead nitrate to 4 moles of NO2, so 0.02 moles of NO2, 0.01 moles of lead nitrate, and 1 mole of O2 to 2 moles of NO3, 0.005 moles of oxygen. And so my total moles is going to equal 0.02 plus 0.005, so 0.025 moles total. And it says that I have a temperature of 300 K and I have a volume of 4.06 liters, so 4.06 to 5 moles. And solving for the pressure, I get a pressure of 0.15 to atmospheres, which is A. 22. We have a mixture of potassium chloride and potassium chlorate. The total mass of the mixture is 1.83 grams. We heat it, and the dry oxygen generated occupied 1.40 times 10 to the second milliliters at STP. We want to know what percent of the original mixture was potassium chlorate, which decomposes as follows. And again, you have that equation on your handout. Okay, let's put our equation on here. Solid, and then O2 gas. And I have my mixture is 1.83 grams. And again, what are we trying to find? It wants the percent KClO3, which is going to be grams of potassium chlorate over total grams of the mixture, which is over 1.83 grams times 100. Okay, so that's what we're trying to find. We need grams of potassium chlorate. And so the thing to remember here is that when we heat this mixture up, only the potassium chlorate is going to be decomposing and producing the oxygen gas. So all of this oxygen gas we have, which is 140 milliliters, which is 0.140 liters at STP, all of that gas came from the potassium chlorate. So if we go 0.140 liters of oxygen, at STP, 22.4 liters is 1 mole of oxygen, and for every 3 moles of oxygen, I need 2 moles of potassium chlorate. So that is going to give me 0.14 divided by 22.4 times 2 divided by 3. So 0.0417 moles of potassium chlorate, and I need grams, so the molar mass, let's see, 39 and chlorine and 3 oxygen, so we should have had a molar mass of about 122.4 grams per mole, which means that many moles is going to be equal to 0.511 grams, and that's the value. So that's the KClO3. That's the value we're going to substitute in up there. And 511 divided by 1.83, that, and then times 100, gives me a percentage of 27.9%, which is answer A. Okay, 23. We have a mixture of 1.5 moles of argon and 3.5 moles of CO2, and a total pressure of 8.5 atmospheres. I want to know what the partial pressure of the CO2 is. Okay, we have 1.5 moles of argon, 3.5 moles of CO2, and our P total is 8.5 atmospheres. Okay, partial pressure of the CO2 is equal to the mole fraction of the CO2 times the total pressure. Okay, mole fraction of CO2 is moles of CO2 over total moles, which is 5 times 8.5 atmospheres. So I'm getting 5.95 atmospheres would be the total pressure, which would round to choice D, which is 6 atmospheres. 24. Consider the following gas samples. I have S2 and O2. Gives moles, gives temperatures, gives pressures. Okay, the volume of, we want to know okay, I'm missing part of this question. Okay, let's see if maybe it's wanting to know which statement is true. Sorry about that. Okay, we'll continue with that. So let's just find which is true. All right, so in sample A, 1 mole, 800, and pressure of 0.2 atmospheres. In B, 2 moles, temperature is 400 K, and pressure is 0.4 atmospheres. So, first A asks about the volume, so let's find the volume. If we pivnert this, I would have so I get a volume of 328.2 liters. And for A, and for B, I get a volume of 164.12 liters. Okay, that's just from using pivnert. And then, so the volume of sample A is twice the volume of sample B. Yes, that would be correct. So A is true. Okay. Let's keep going because the question might have been which one is false. I don't know how this thing is keyed. So the average kinetic energy of the molecules in sample A is twice the average kinetic energy of the molecules in sample B. That would be true because the temperature in A, the Kelvin temperature, is twice as high. The fraction of molecules in sample A having a kinetic energy greater than some high fixed value is larger than the fraction of molecules in sample B having kinetic energies greater than that same high fixed value. Well, that would be true also because if the temperature of A is higher, then the average kinetic energy of the particles in A would be higher. So if we had some kinetic energy value, the fraction of molecules in A that exceeds that value is going to be greater than the ones in sample B. Okay, so C is also true. D, the mean square velocity of molecules in sample A is twice as large as the mean square velocity of molecules in sample B. Okay, this is going back to the equation that we used, but not like I think you used it in your online homework, but it is the root mean square velocity, and that is, if you remember, the square root of 3RT over the molar mass. And so for this one, for D, and looking at that, let's see, S2 would have, this is S2, so its molar mass is going to be about 64 grams per mole, and O2 is approximately 32 grams per mole, and so let's see what we get then. This is molar mass in kilograms, so it's twice, the molar mass is twice as large, so, well, no, it wouldn't be anyway, because the molar mass is in the denominator, so the velocity of the molecules in sample A would be lower than the ones in sample B. So we really didn't even need that equation for that, because the A molecules are larger and are going to move slower anyway. So D is false, and then we'll just continue with these equations, or these statements. Assuming identical intermolecular forces in the two samples, sample A should be more nearly ideal than sample B. Sample A is at a higher temperature and a lower pressure than sample B. So E would be true regardless. I mean, if the intermolecular forces are similar, then we look at the conditions, and we know that a gas is more likely to be ideal at high temperatures and low pressures, well, and lower numbers of moles also. So sample A would, based on its conditions, be more likely to be ideal than sample B. Okay, a sample of nitrogen gas is contaminated with some other gas, and we have a partial pressure of each gas, and they're allowed to effuse through a pinhole, and it's found that gas A escapes at 3 times the rate of the nitrogen, and I want to know what is the molar mass of our unknown gas. Okay, so the information we're given is that pretty much these gases are they're under the same conditions and the same number of moles, because our pressure and our temperature, and they're in the same container, so the volume is the same, so the number of moles is going to be the same. So all that initial information is really just there to tell you these things are under the same conditions, same number of moles. And so the only thing that's going to affect their rate of diffusion then is going to be based on Graham's law. And so if the rate of gas A over the rate of nitrogen is 3, gas A escapes 3 times faster, so that's what that means. And we know Graham's law says that the ratio of the rates is inversely proportional to the inverse ratio of the square root of their masses. So 3 is, nitrogen would be about 28 grams per mole over square root of the mass of A. And so the square root of 28, oops, divided by 3, square that. So that gives me mass of A of about 3.11 grams per mole, which is choice A. All right, use kinetic molecular theory of gases to predict what would happen to a closed sample of a gas whose temperature increased while its volume decreased. Okay, we want to know what would happen if my temperature is increasing, my volume is decreasing. Well, in looking at what would happen to the pressure, temperature increase would increase the pressure. Volume decrease would increase the pressure. So choice B would be correct. (27) Which of the following would have a higher rate of fusion than C2H2? And we are assuming that these gases would be under the same conditions to make this comparison. Okay, so higher rate of fusion implies a lower mass. Okay, so C2H2 is around 26 grams per mole, and so we're looking at one of these, and the only one that's less than that is the methane, which is approximately 16 grams per mole. So choice D would be correct. (28) Which of the following is true about kinetic molecular theory? So looking for the statement that's true. Okay. Statement A, the volume of a gas particle is considered to be small. Actually, it's considered to be negligible or zero. So A is not true. B, the pressure is due to collisions of the gas particles with walls of the container. Yes, B is true. Okay, then just continuing on, the gas particles repel each other but do not attract one another. No, kinetic molecular theory says no interactions, no repulsions or attractions. Adding an ideal gas to a closed container will cause an increase in temperature. No, it says that temperature is proportional to the average kinetic energy. We're not changing the energy, so we're not going to have an increase in temperature. And at least two of the above are correct. No, that would not be true. Okay. 29. Which of the following statements is true concerning ideal gases? All right. A says the temperature of the gas sample is directly related to the average velocity. No. The temperature is proportional to the average kinetic energy. B, at STP, 1 liter of argon contains about twice the number of atoms as 1 liter of neon. Since the molar mass of argon is twice that of neon. No, at STP, 1 liter of the gas, so we have same temperature, pressure, and volume. That means moles are same. Doesn't matter what the molar mass of it is. C, a gas exerts pressure as a result of the collision of the gas molecules with the walls of the container. Yes, that's true. And D, we talked about this before, gas particles in a sample exert attraction for one another. No. Ideal gases says that they do not affect each other. Okay, that is